All right, welcome to section 1.2 for Workplace and Apprenticeship 30. Today we are going to be looking at the equation of a line, whereas last time we were together we talked about what is a linear relationship, how does that relate to slope, how does it relate to being an independent variable and a dependent variable. And all that we're going to look at today is how do we come up with an equation that is a function of y and m and x, and how do we relate that to what we already know? That's what we're going to be doing. So to start off with, let's look at something that we already know about. We know how to do some conversions from previous math classes, and a common one that we're going to end up doing is the relationship between a mile and a kilometer. How do we change miles to kilometers? And just so you know, this information you might want to jot down for your own information, but that's completely up to you. When we talk about the relationship between a kilometer and a mile and the multiplier, what it means is that to find the amount of, is it kilometers in a mile or is it centimeters? It's kilometers per mile. We would take our kilometers, which I'm going to use K, and that equals the number of miles multiplied by 1.609. So that M stands for miles in that expression there. So if you ever want to figure out how many kilometers are in a mile, simply multiply by 1.609. Similarly, if we look at centimeters to inches, if I want to find out how many centimeters there are in an inch, the centimeters is the conversion factor, which is 2.54 times the number of inches. And so this rate of change number can be related to this y equals mx idea, where m is your rate of change, and for these it's the multiplier, and this green one will be like your x, which is your independent variable, and then on the left hand side we have our dependent variable. The centimeters depends on inches, the kilometers depends on miles, y depends on x. And so that's an equation for a linear relation. A similar situation here we can look at graphically is a vehicle that starts at Moose Jaw and heads to Thompson. So you can see I didn't label my axis very well, not displacement, sorry, I want distance on that side. So that's distance, and that's measured in kilometers. We have time, that's measured in hours. And we have the title, Moose Jaw to Thompson. When we look at this, there are some things that are going to apply. First of all, the equation is simply relating your rate of change number, which is 90 kilometers per hour, to the other variables. And we see again the independent variable is time, which is here. We have a dependent variable, which is the distance, which is the vertical one. And the rate of change, the slope of this graph, if we were to figure out the slope, we would find that the answer would be plus 90 because the vehicle is increasing at 90 kilometers per hour. There's also some partial variations we're going to deal with here. Right away we know this is a partial variation because this repairman starts off charging $95 right away. And then with every hour that passes, the total goes up by $75 per hour. So I know it's a partial variation because we don't start at zero. And what we can do then is relate this relationship to the rate of change and then to an equation. So again, we see the increase here as a constant $75. And you can see, just as a side note, that as the time goes on, your amount per hour decreases simply because you're not making that $95 every hour. So what is the rate of change? In this case, that is the $75 per hour, which is the same thing as your slope. So that rate of change is the slope value. The flat rate is talking about the original amount, which is the $95. The independent variable is the one that determines the earnings, which in this case would be our time. Our time determines the earnings, so that would be the independent, which makes the earnings the dependent. Is this linear? Yes, it is. And in fact, if I want to make the equation, the earnings is the rate of change multiplied by the independent variable, which is the time, plus the place where you start at, which is your flat rate. So very similar to what we looked at earlier with y equals mx, where your 75 is your m. Now we add on this b value, which is 95, and you'll see in the next question, all that ends up being is the place where the graph crosses the y-axis, which we call the y-intercept. And this is the same graph right here, and we see that right there is your 95, that's your y-intercept, and at any point here our slope is, or the rate of change is $75. Every time the time goes up an hour, the rate of change or the earnings go up $75. So again, just to review, this is a partial variation. Why? Because it doesn't go through 0, 0. What's missing on this graph? Well, I don't label my axes for some reason. I must have got lazy, and I don't have a title. Make sure we have those. This is just another problem. You're going to have to start picking out information from problems. This is about a pool that's emptying, and what we're told is that at 2:30, the depth is 32 centimeters, and as it empties, the depth decreases. So 45 minutes later, it's at 11. And so if it continues at that rate, clearly this isn't possible, but mathematically anyways, we're going down 21 centimeters. If I go down another 21 centimeters in the next 45 minutes, theoretically you're below the pool, but really that means the pool's already empty. And one thing that you're going to have to do then is to relate this expression to an equation and also to a line. So again, the time determines the depth. As time goes on, the depth changes. So the depth is decreasing at a rate of 21 centimeters every 3/4 of an hour, multiplied by the amount of hours. And then the starting point is at plus 32. Now if you divide 21 by 3/4, you will find that you get your actual slope. So I'm just going to do that and get my answer there, which is 28. So I'm going to just erase that and say, well, really that's dividing that out. 21 divided by 3/4 is 28. So that's minus 28 centimeters per hour. So I have my relationship. If I were to look at this as a graph, I'm not going to do it perfectly just to save a little bit of time. It starts at 2:30, now we're at 3:15, and then another 3 blocks, we're at 4 o'clock. And at 2:30, let's go up by 5, 10, 15, 20, and then 30. At 2:30, we're at 32 centimeters. At 3:15, we're at 11. Again, just estimating here, and we can see that clearly at 4 o'clock there's a problem. Now what if the question asks you, well, how would you need to change this situation so that it ended exactly at 4? And those are some of the questions you're going to have to deal with. So a lot of them you're going to get 2 pieces of information, and you can see even in this question quickly, we've got degrees Celsius and degrees Fahrenheit. In the next question, you've got money, $8 per use, $2 per use, yearly membership fee. You're going to have to pick out the numbers and create equations, and it's all related to the rate of change and where it crosses the y-axis. And I like to sketch the graphs out. You're going to have to determine if that's what you want to do. I didn't see any definitions in the textbook. You should double check to make sure I'm right. Here's where your assignment is on Build Your Skills. Don't forget your instructions there. You need to do all of them up to the extent, and then you have to pick one. Sometime during this chapter, you have to complete a math on the job to add to your portfolio. Either way, when you're done this section and you're comfortable, you know what you're doing, you're welcome to grab the check from me, and I will check and see that you're on task and you know what you're doing. And if that's the case, then you can move on to the next section, 1.3, and then before you know it, you'll be done chapter 1. So that's it. Talk to you again soon.